even started yet.
Okay. I think you would be having microprocessor, VLSI, and DSP. You are having now in this
Yes,
semester.
sir. Yes, sir.
DSP and two more subjects. Which one? Okay, there would
So
be.
actually, we don't know the full forms actually.
Okay, do you know the name? What is the name? Okay, anyways, let us leave that thing. Okay, so you are having five subjects in this semester. Okay, and labs. How many labs? Four labs, I think. Right?
Three, sir.
Hmm? Hello.
Sir, it's three, sir.
Okay. So let us talk about our subject. Okay. So this is named as. I think I have started the recording. Yes. Okay. This is named as integrated circuits and system. Okay. Earlier it was called as VLSI design, VLSI engineering. So till last year, okay, the name of the subject was VLSI engineering, VLSI design. Okay. But from the current year, in the new syllabus that was implemented from 2019, I think. Okay, the subject name has been changed to integrated circuits and system. Okay, although the syllabus is similar, okay, there is a little bit of change in the syllabus. Okay, there are some new topics, some new relevant topics that are added. Okay, and some few topics might have been removed from the old syllabus. Okay, so the syllabus is also new. Okay, and it contains 5 modules. Okay, and there are some textbook and reference books mentioned here. So just let I will just go through the syllabus. Look at the course objective. What is the objective of this course? To understand the fabrication process of CMOS technology. Fabrication process. Okay. But in the starting, I would like to tell you that this course, Integrated Circuits and System, that is ICS. Okay. The main aim of VLSI is to fabricate a chip. Okay. So there are various kinds of chips that are available in the market. For example, microprocessor that we are using in our laptops, computers is also a kind of chip. Okay, the chip that you had used in your basic electronic labs, if you remember, there was chips for AND gate, OR gate, NOT gate, XOR gate, 7400, IC 7402, or IC 7408, like that. Those are also chips. Okay, so there are various kinds of chips, and that is the ultimate aim of this field, VLSI. Okay, and in this industry, there are various kinds of companies that exist. Some are involved in the designing part only, some are into fabrication only, and there are various other things. Okay, so the fabrication process of CMOS technology, because CMOS technology is presently the dominant technology. So we will try to understand the fabrication process of CMOS technology. Okay, and the second one is to study digital circuits using various logic methods and their limitation. Okay, you have covered the subject on digital electronics, analog electronics, and basic electronics, right? So you are well aware of these subjects, so that will form a foundation for this subject. Okay, those concepts will be used here. And the third objective says that to highlight the circuit design issues in the context of VLSI design. Obviously, the lab will consist of the designing part of various circuits. Okay, we will see uh, both the digital circuits and analog circuits, that how are they designed using different tools, that will be covered in the lab. Okay, but as far as this syllabus is considered, the module 1 will be about the introduction part. It will introduce the VLSI systems, VLSI thing. Okay, and then the some of the concepts that are used, some popular VLSI design methodologies, and what are the various, and it will also contain fabrication process, topic on NMOS and CMOS fabrication process. Okay, and what are the design rules that are to be followed while fabricating some sort of chip. Yes, it will start from the introduction and will go into the fabrication process steps. Okay, and then the second module will start with the transistor, MOS transistor. Okay, now remember one thing, that in VLSI, the most important device is MOSFET. Okay, metal oxide semiconductor field effect transistor. Okay, more than 95% of the VLSI chips are being manufactured with uh, using this device, MOSFET. Okay, so MOSFET is the most fundamental device that is being used, okay, in manufacturing these ICs. Whether it's a microprocessor IC, it's whether it's a DSP application IC or some any other kind of IC, you will see that at the bottom there would be some sort of transistor sitting there and operating. So by this way, in this context, we should have a clear-cut understanding of the operation of MOS transistor. Okay, so this module 2 will try to uh, cater to that need. So we will see the operation of MOS transistor in detail, and obviously MOS is a transistor, MOSFET is a transistor, and by using this transistor, different circuits are made. For example, the different gates, okay, inverter, NOT gate, OR gate, AND gate, XOR gate, XNOR gate. These all gates are made up of by using transistor, MOSFET. Okay, and among all these, the inverter is the most fundamental gate. Okay, okay, and we will study about the MOS inverter characteristics, since this is the most fundamental gate. Okay, and if we know about this inverter, then we can easily understand the behavior and characteristic of other gates. And MOS inverter static characteristic and dynamic characteristics will be introduced in this module too. Okay, then after studying these things, after developing the fundamentals of VLSI design, then we will in module 3 we will look into different kinds of logics that are available for designing various chips. Okay, so digital CMOS logic design, then it will cover combinational logic circuits, flip-flops, then NMOS logic, transmission gate logic, and dynamic CMOS logic circuit, domino logic. So these are all different logic families, okay, uh, using which we can design the circuits. And all of these different logic families have got certain properties, certain advantages and disadvantages. So depending on the requirement, okay, our kind of logic family is chosen for a particular application. Then NORA CMOS logic, zipper CMOS logic, fast transistor logic, complementary fast transistor again, there are different logic families. Okay, so we will see about these different logic families in module 3. Okay, then module 4, I think timing analysis. This will introduce about the delay in the circuits, that because if some sort of circuit is designed, okay, there are some parameters upon which it will be tested. The main parameters are being the speed, power, and area. Okay, speed, that how fast does it operate, power, that how much power does a chip consume, and area, and how much area a circuit acquires. Okay, so one of the parameter is speed, and speed is measured in terms of delay. So we will see the delay in VLSI circuits, the delay in CMOS inverter, okay, and some topics related to it, rise and fall time, these things. Then there would be an introduction part about the physical design of IC. We will see what are floor planning, placement, routing, and there will be an introduction about this BiCMOS technology. Okay, look, I said that CMOS technology is popular, very much popular. Okay, but for certain applications, very few certain specific applications, BiCMOS technologies are also used. Okay, so we'll see how what is the BiCMOS technology, what is the circuit for this, and some basic gates depending on constructed with the help of BiCMOS. Okay, so mainly it will focus on the timing analysis and BiCMOS technology introduction. Okay, then in the last module we'll cover two topics broadly. The first one will be about testing the chips. Okay, so once we have fabricated a chip, it needs to be tested before launching it in the market. Okay, anything that you design, any product, if you are having any product, if you design, you cannot launch it in the market directly without testing, because you don't know whether this fabricated product will work properly or not, unless and until it is tested. Okay, so testing is a requirement, and since these chips contain huge number of transistors, in millions of numbers of transistors, so testing these chips is also a huge task. So there are various strategies developed for testing these ICs. There are various models. You will see what are fault models, fault simulation, design for testability, ad hoc testing, scan test, then BIST. So these are all types of testing that are there for testing those chips. Okay. We will see this thing, okay, in module 5, and this is the newly added here portion, I think. Digital design using Verilog. Okay, we will be using Verilog language in our uh, labs, VLSI lab or ICS labs. Okay, so introduction, then Verilog, naming conventions, operators in Verilog, data types, behavioral modeling, structural, then combinational and sequential logic. We will see these things. Okay, and we will be using Verilog language for designing circuits in our labs. So take a note of it. Okay. Okay, so there are two popular languages, Verilog and VHDL. Uh, we will be using Verilog, okay, and these two are interrelated, like similar. If you learn one language, you can easily switch on to the other one. Okay, so so module 1 is about introduction, then module 2 is about the transistor and the inverter. Module 3 is about the different logic families. Module 4 is about the timing analysis and BiCMOS. And module 5 will be about VLSI testing. Okay, so it's going like this, from the device to the circuit to the testing. Okay, so we need a device for designing a circuit, and after designing a circuit we need to fabricate it, and after fabrication we need to test it, and that is how the VLSI design flow uh, happens. Okay, so this is the syllabus for your ICS, and the books that they have given here is obviously we will be following some of these books, okay, more, and the first textbook, and that is Kang and Leble Bisi. Okay, CMOS Digital Integrated Circuits. This will be one of the main books. That is the textbook number one. This one, and reference book number two. This one. This is Digital Integrated Circuits by Rabe, John M. Rabe and Chandrakashan. Okay. So these two books will be the main books that I will be following for covering this syllabus. The first book is by Kang, textbook number one. Take a note of it. And second book is by Rabe, reference book number two. Okay. And these books are available for download on internet. You can find the PDF version of these books. Okay, these are available for free download, so you can download it. Okay, and then there are some other books mentioned. Textbook number two is by VLSI Design by D. Das. Okay, this also introduces all the topics in a basic sense. Okay, it introduces many topics. Okay, then there is one very standard book, I would say, that is by West and Harris. This one, CMOS VLSI Design, a Circuits and Systems Perspective. But this is this will be difficult to understand for a beginner. Okay, but although this is a very, I would say, very good book. Okay, but for some topics I may refer to this book also. Okay, I will tell you for what topic to refer from which book. I will tell you about this. Okay, then there is one book by Palnitkar. This is about Verilog SDL, a guide to digital design and synthesis. Okay, don't worry about this. You can refer to this, but we will learn the language along with as well as we progress in the lab. Okay. Okay. Then there are certain outcomes of the course. Okay, that what things you will learn from this course. Okay, so these things are expected from you after we cover this syllabus. Okay. So any doubt from the syllabus point of view? Anything that is not clear? Take note of the book, which books are main, the textbook number one, and the reference book number two. Okay. Hello, students. Are you listening?
Yes, sir.
Okay. If anyone is having any doubt, he or she can ask anytime. Okay. So that will give me confidence that students are listening. Otherwise, in online mode, we are not sure whether students are listening or not. So if students ask doubts in the lecture, then it actually motivates the teacher. Okay. Okay, so this was about the syllabus part, and okay, this is the old syllabus. But anyways, and let me start with the introduction. Okay, I will start slowly. Okay, so let us see. Okay. Introduction. So the term that is important is VLSI. Okay, VLSI. What does this term stand for? The VLSI stand for, many of you might be knowing that it stand for very large scale integration. Okay. Integration of something on a very large scale. Integration means, we know that integration means to add up the things. Okay, but here integration is of components, of integration of transistors, that is to add more and more number of components and or transistors on a given chip. Okay, and this integration occurs on a very large, very huge scale, and that is why the term is like this, very large scale integration. Okay, just for the reference, because I will be using these terms. Look, the at the most fundamental part there will be the device. Okay, and which device? In most of the cases it will be MOSFET, the metal oxide semiconductor field effect transistor. Okay, now using various devices we can construct a circuit, right? So circuits like adder, subtractor, multiplier, like those circuits. Gates also we can construct by using devices. Okay, now by using different circuits and combining them properly, interfacing them properly, we can construct a whole system. Okay, like a chip, a microprocessor. Okay, the whole chip. So device, if I say device, it means I'm referring to some kind of like MOSFET device. Circuits are those things which are made up of various numbers of many number of devices or MOSFETs, like adders, subtractor, multipliers, dividers, and various other kinds of circuits. Okay, and system would be something big or huge. Okay, that will do certain kind of application. Okay, and system will be formed by connecting various kinds of circuits in a proper fashion. Okay, so here I'm referring to a very large scale integration of what? Very large scale integration of the device, the MOSFET. Okay, so the manufacturing large number of components in a given area, the area is limited. Okay, so for example, the microprocessor that we are using in our computers. Okay, if someone has seen the actual microprocessor, he or she will agree that the actual size of microprocessor is not bigger than this. Okay, this is the actual size of microprocessor that we are using in our laptops. Okay, actual size. And and this area, okay, this area contain more than 1 billion number of transistors or more than 1 billion number of MOSFET. Okay.
Excuse me, sir. Yes, sir.
Uh-huh. Yes.
No, the screen was not visible, sir, but now it is visible, sir.
Okay, okay, okay. So this small size, this small area contain more than 1 billion number of transistors. Okay, now imagine how those how the devices are present here that are in number more than 1 billion, billion. Okay, so the area is not increasing. My point is, with each new generation the area of the chip is not increasing. They are not increasing the area in the same area, but they are increasing the number of transistors that are manufactured, that are fabricated here. So area remains same, but with each new generation, with each new technology, okay, the number of transistors that are present on the given area, that increases. Okay, the first microprocessor that was introduced by Intel, that was 4004. Okay, it contained around some few thousands of transistors, and now it contains more than 1 billion number of transistors. The size of those, the that IC and this IC would be approximately same. Okay, but there is a huge difference in the in the number of or integration of devices here. Okay, so manufacturing large number of components in a given area. The main target of integrated circuit design and fabrication is to achieve more functionality at a higher speed using less power, less area, and low cost. Okay, obviously we want that with each new improvement we would like to have more functionality. Okay, we would like the chip to perform more and more function at and higher speeds using less and less power, using less area, and it should be cheap also. The cost should also be low. Okay, so these are all the desirable things there there that everyone wants from a chip. But remember one thing: all of these things cannot be satisfied uh, for a single chip. Okay, all of these things cannot be satisfied in for any particular design. Okay, so some applications, so it depends on the application which parameter you want to go. Okay, some application demand high speed, some application demand low power, some application demand less area. Okay, like that thing. For example, the devices which are operated on battery. Okay, so there power constraint power is a constraint because it's operating on a battery on some remote location. So if some gadget is operating on battery at a remote location, so the power naturally becomes a constraint. So for those applications we would like to design a chip that will consume less power. Okay, although the performance may be secondary, but the primary thing would be to consider about the power. Okay, and for some applications higher speed is a requirement. Okay, for example, the things or the calculations that are occurring in let's say in stock markets, there we require high speed, very high speed real time calculations. Okay, so there this power consumption and area may not be a constraint, but speed is a constraint. Okay, so the main focus would be to design a chip which would operate at the highest possible speed, and power and area may go in the background. Okay, so depending on the application, okay, the ICs are designed, and there is a trade-off between speed, power, and area. If some parameters are improved, the other parameters get deteriorated, and vice versa. Okay, so there should be a trade-off. It should be designed depending on the type of application where the chip will be used, right? And in the year 1958, let's start in the 60s, the first monolithic IC, okay, was there, where the level of integration was 1, means it contained just one component. Then in 1962, a multifunction IC came that contained a few number of components. Okay. Then similarly in 1967, as the technology improved, we call this as MSI, medium scale integration, where the number of components rose to something between 20 to 200. Okay, and similarly in 1972, LSI, large scale integration came. So those chips which contain something around 200 to 2000 number of components, those were categorized as LSI chips. And in 1978, VLSI chips came, the chips which contained between 2000 and 20,000 number of components, uh, between 2000 and 20,000 number of logic blocks. Okay, and in 1989, ULSI, ultra large scale integration, were those chips which contain more than 20,000 number of logic blocks. And this trend continued. And now we have chips which contain more than millions of blocks. Okay. So, although the things have improved very much since 1978, okay, but the term is still popular. This VLSI term is still popular, and it remained popular, and hence we are still using this term VLSI even for the newly designed chips. Okay, so regardless of the term used here, okay, VLSI will refer to any kind of chip which contains a huge number of components. Okay, so this is the chronology of evolution of the ICs, and look at this. This is what this. I have taken the image from a book. This is a mechanical calculator. Okay, this is a mechanical calculator, right? Working part of Babbitt's difference engine that was developed in 1832. Okay, this was the first known automatic calculator, and it had 25,000 mechanical parts. Okay, it had 25,000 mechanical parts, and the cost was around something more than 7. पावर भी चले जाता है कभी कभी. Okay, the power was cut here in the college, so I am connected via mobile. Okay, so I am giving this example. Look at here. Just to give a reference that look at this mechanical the design is big. Okay, and it's a mechanical device, completely mechanical device. Okay, and it was costly. Okay, contained 25,000 number of mechanical parts, so the size was big. It was costly. Okay, it was 17,000 pounds in 1834. So how much it will cost in 2021? You can just easily calculate. Okay, so the thing is here. So at that time, the mechanical engines were there. Okay, but the size was big. The cost was high. Okay, so naturally, the engineers and scientists were searching for some alternative solutions which could function faster, and which could also consume less area, and maybe cheaper also. Okay, so electrical solutions took over because electrical components does not contain any moving parts. Okay, and look at this image. Okay, this will contain mechanical parts, and any mechanical device which contain mechanical or moving parts is subjects to wears and tears with time. So it will wear out in few years. Okay, so there are uh, very big limitations when using a mechanical device for calculations. Okay, so So the thing was to develop something from by using electrical or electronic devices, okay, which can work faster, which would be small in size, okay, and which would be cheaper also, obviously. Okay, and hence when the transistor was invented in 1947 by invention of transistor. Okay, so they shared the Nobel Prize for inventing transistor. So right then, people knew that what was the significance of this device that was being invented, because they knew that this is going to change the shape of future. Okay, now we have all those microprocessors that are based on these devices. Okay, although earlier BGT was more popular than MOSFETs, but later on MOSFETs took over BGT. Okay, but anyways, the evolution occurred right from there. Okay, and this is the first image of the BGT that was being designed by these scientists at Bell Labs. You may not be able to uh, connect to this, but this was the actual design. Okay, then single transistor IC, then CMOS logic gates, and the first microprocessor in 1970, the Intel 4004. Okay, this is the image. Okay, at that time there was not much automation. Okay, so many of the things were to be designed by using hands. Okay, so we can see different components that are placed here. The wirings were also done with the help of wires. Okay, and this contained around 23 number of MOS transistors, 2300 MOS transistors, the first microprocessor from Intel in 1970, and this operated at around 740 kilohertz of frequency. So now we have the device, we have chips that would look like similar to this. Okay, and it will contain more than 1 billion number of transistors, and it will operate at more than 1 gigahertz of frequency. So 1 kilo is 10 to the power 3, and 1 gigahertz is 10 to the power how much? Yeah, how much 1 gigahertz?
Nine, sir.
Hmm?
So 10 power 9.
10 to the power 9. Yeah, I'm not able to write properly. Okay, 10 to the power 9. So there is a huge difference. Okay, so okay, I will go to this. Yeah, this one. So this is a graph that tried to shows the market capture. Okay, in 1975 it was something around $4 billion. Then it increased exponentially almost. It is increasing like this. Okay, in 2002 it was to be around 288 billions of dollar. Okay, and we are 20 years ahead, so right now we would be somewhere here. Okay, in trillions of dollars. Okay, And just now Apple, that is a very big company. Apple, I think, was the first trillion company which achieved a market capitalization of more than $1 trillion. Okay, so the market is huge, and the market is growing very rapidly in this fashion, non-linear curve. Okay, and this is all because of the things that they offer to the mass, to the public, and public is also consuming those things. So
Sir,
there's a continuous supply and demand thing here. Okay.
sir,
Yes.
sir, from a recent study, it is seen that Apple is using the components of different companies like Sony, Nvidia, and uh, Samsung, etc.
Okay.
So the processors, the micro, whatever they are using, they are from different company, and their total, making charges were about $3,300.
Okay.
So why are they costing so much, sir?
To make profit.
Even then, we are not as fools that we are ready to buy like whatever amount they are ready to pay. They're asking.
But the thing is that Apple is the most popular, one of the most popular company in the world. Hmm? Although we are not using much in India, but in Western world, in Europe, they might be using it very popularly.
Sir, if we
Okay.
know the secret behind the components, then aren't we able to copy it and develop a own generation of Android which has that all facilities?
There was a company called Micromax. Okay, that was an Indian company that did well in it initial some years, but then it collapsed. Okay, what was the reason behind it? The main reason was R&D. It was just assembling the phones and selling it in the market. It was not doing its own research and development, R&D. Okay, and that was the reason it failed. But it was a good company. It was a popular company. Okay, many people used to buy its gadgets. Okay, and these
Yes,
companies
sir.
like Apple, Samsung, Sony, they have their own R&D houses. Okay, so they do their own research, and uh, no single company does all the thing in the world. Okay. Okay, some are more specialized in designing, some are more specialized in fabrication, some are doing just assembling part. Okay, so there are various categories of companies. There are various kinds of vendors. Okay, some are totally in the designing part only. So when you design a part, you also need to fabricate. So when you need to fabricate, you will take the help of some fabrication company, obviously. So you will have to take the help of some fabrication industry. Okay, so you will transfer, you will give your design, you will give you you will give your design to the fabrication company and will ask them to fabricate that chip. They will fabricate it for you and then send it to you. Obviously they will charge something. Okay, so for each of those segments there are specialized companies. Okay, Apple is doing what? Apple might be use look, Apple cannot develop its uh, all sorts of things that are used in a single mobile phone. Okay, in a single mobile phone, various kinds of chips are used. uh, Screen contains some specialized glasses, then cameras are there, sensors are there. Apple cannot manufacture all of those different kinds of things, so it is buying from different specialized companies. Okay, and obviously it is also doing its own R&D. Okay, so by combining all those things along with its own R&D, okay, it is trying to develop a good device, although it may be a bit high on the cost. Okay, but there are some people who are buying it and using it. Okay. So this is the thing, and we are moving from large centralized expensive devices to small portable distributed inexpensive devices. Now we have different kinds of gadgets. We have wearables, we have smartwatches that we carry on our hand. Okay, so those are small, those are portable. Okay, but they are also intelligent. They contain some sort of chip inside those things. Okay, so this is the trend, right? And just for example, I have given here Intel Pentium 4 chip was developed. Do you have a class now? Do you have any other subject class now? Because the time is, I think, over 11:30.
No, sir.
Oh, okay. Then give me just 5 minutes. I will wrap up the class. So Intel Pentium 4 chip was uh, fabricated using 0.13 micrometer process. Process or technology means same here in VLSI. So 0.13 micrometer or 130 nanometer. Okay. So every technology or process has got some numbers attached with it. So that number will specify the smallest transistor, the size of the smallest transistor that can be fabricated on a chip. So if the process is 0.13 micrometer process, it means that the size of the smallest chip, the size of the smallest transistor that would be fabricated on the chip would be of this size. Okay, it contained around 55 million transistors, and this is about Pentium 4. This was around 15-20 years back. Okay, 15 years back, and it operated at 2.4 gigahertz frequency, and it contained an area of just 145 millimeters square. Okay. Similarly, there was an IBM S390 microprocessor that was again manufactured with using the same technology, 0.13 micrometer CMOS process. It used 7 layers of copper metal interconnects. It contained around 47 million number of transistors. Okay, and it operated at around 1 gigahertz of frequency. The size was 180 millimeters square. Okay, so although these are not very recent, but again, if we look at these specifications, look, it contained around 55 million transistors. 55 million transistors means 10 lakh crore, more than 5 crore number of transistors on a single chip. Okay, so the things are very like attractive here. Fantasy, 2.4 gigahertz of clock frequency, and on just 145 millimeters square of size area. Okay, so I mean to say that the technology is very sophisticated. Okay, and the present day microprocessor chips contain more than 1 billion transistors, more than 1 billion transistors. Okay, so the things are very on a very high scale it's occurring. Okay, okay, so this is the last so this is about introduction. Okay, this is trying to give you some idea that how the industry has grown in the last some 5 or 6, 7 decades. Okay, so this shows the number of transistors per chip. Okay, for a microprocessor and for memory chips. Okay, again, right from 4004 to some Pentium, it grew like this. Okay. And for memory, it grew a bit faster as compared to microprocessor. There is a specific reason for this, because memory circuits are highly regular. They contain repetitive structures, and that's why it's easier to make more dense architecture in memory chips as compared to microprocessor chips. Okay, so there was called something called as Moore's law. A person called Gordon Moore, which co-founded Intel. Okay, and in 1960s he predicted that the number of transistors that can be integrated on a single die would grow exponentially with time. So from the observation, the integration complexity doubles approximately every 1 to 2 years, or approximately every 18 months. So number of transistors doubles every 18 months. Okay, so this statement was given by Gordon Moore, and he predicted that thing actually. Okay, and when we analyze the things by drawing a graph, and when we see that this prediction was very much close to this progress. Okay, so this came to be known as something called as Moore's law. Okay, that is the number of transistors on a given area doubles approximately every 18 months. Okay, and this is very popular law in VLSI industry, and right now also the industry is following this law. The market has grown like this, grown around this Moore's law. Now they are targeting their devices in the future by keeping this law in their mind. Okay, that we have to release the next component, next new device after 1.5 years or 2 years. Okay, so they try to develop their research and all those things accordingly. Okay. Okay, so from the next class we will see about this layers of abstraction and some other things. So this was about introduction of this VLSI. Okay, so you can ask your doubts here. If you have any doubts, anything you want to discuss, uh, you can ask. And for attendance part, okay, Jagat Jeevan has asked, sir, why don't we learn ULSI instead of VLSI, as ULSI is the latest technology? Okay, ULSI is just a term. Okay, VLSI is also a term. Nowadays, you can give any, like after ULSI, GSI came, giant scale integration. So all these things means that the number of components are growing on a chip. So it is not something that VLSI is older than ULSI. No. Still, we are using VLSI because this term became popular. Okay, and it continues to remain popular. Although the technology is growing, but this term is still being used for the current technology also. Okay, the current technology is also described by using this same term VLSI. Okay. Then okay, you can give your attendance in the chat box. Just type your roll number and name and post it in the chat box. For attendance, type your roll number and name in the chat box. Okay. ये इनका पेज रजिस्ट्रेशन का इनका क्या सिस्टम बनाया इन्होंने 5 दिन में एक ही दिन काम किया बाकी 4 दिन ठप माइक ऑन